Okay, well, hello everyone. Thanks for coming to my talk. Today, the title of my presentation it has to do with something that we have seen during the last years that is bringing a lot of attention and has to do with applying systems engineering principles to mitigate risks in hydrogen and derivatives project development. A little bit of my background. I'm the country manager of HINICIO in Colombia. My background is chemical engineering, and I'm specialized myself in energy systems. 10 years of experience in consulting and in engineering also, and about 6 years, so since 2017, I've been working in hydrogen and derivatives projects across Europe, Middle East also, and Latin America. Well, and now here in the US. So my agenda will be for the following 15 minutes. We will see what's the challenge we are seeing here to develop this type of projects. Then I'm going to explain the systems engineering approach that we have developed to solve this issue. And then I'm going to show you a case study. Okay, so it's easier to digest all this information. Okay, first of all, well, at HINICIO we have developed more than 600 projects worldwide since 2006. Our headquarters are in Brussels, and these projects have been developed in more than 30 countries. So, if you want to know more about it, we have a booth here in the conference, so feel free to go and join us. Okay, let's talk about the challenge now. As you see here, and I would like you to look at the figure on the left side, we have a huge challenge in terms of the gap to target that we see for 2030. At the moment, there are 320 billion in between all the projects, including those announced. And we need to double that amount to be able to achieve the carbon neutrality for 2050. So the big question here is, how do we get from the announced projects, how do we move them to the further stages? So pre-FEED. FEED, for those who don't know, is a front-end engineering design, and then FEED, and then the other FEED, which is the final investment decision. So I have to congratulate North America, because from the committed investment already that we can see that there are 29. We see that already 10 of them are in North America, right? So even though Europe leads on announcements, it's North America who is leading in committed investments. So to understand the challenge, this is very, very important. We have here the business as usual case. This is how you develop projects usually. And what do we do when and I can give you the example of ammonia, for example. So existing market. What you do is you look at the existing market, you take a share of it, and then you say, okay, I'm going to be able to cover that amount of ammonia, and with that, you design your plant capacity. So it's a CapEx-driven approach. Once you have your plant capacity, you go on the operational design and the permitting and regulation, and you are able to finance your project, okay? On the other hand, when we look at the clean hydrogen, we see that the first step is not the existing market anymore, because there is no existing market for clean hydrogen, but it is policy and regulation in this case. And what this means is that it's through policy and regulation that we go and see the future market, right? Because it has to have the right attributes to do this. Then we go and see the operational design that has to comply with the requirements that the regulatory framework is asking or is requesting to your client, and the funding and project finance, because, well, we are seeing all the incentives that are worldwide, right? And it's when you have that, You go and you can certify your project, or you can define your plant capacity, so at the end it's more a function of the OpEx. You need to know how to operate to define your size, because sometimes your size can be actually oversized. And for the certification case, we have to be aware that you can have a one molecule of ammonia, but one molecule can have many attributes. That means that for one molecule of ammonia, you can have one price, and for three other, you can have three different prices depending on the market that you are dealing with. So, just to make clear, capital-driven approach, policy-driven approach. We have a few unknowns here, and then there are several unknowns because of the iterative characteristics between the operational design and the plant capacity. Okay, so look now at on the right side, and you will see many of the topics that you usually have to deal with when working with systems engineering. And this is what we call systems engineering. We have a system in which there are many topics interrelated to each other, so it's not that easy to move forward in these stages that I've just presented. And the main question here is how to architect a system of systems that satisfies all the stakeholder requirements. This is complex because we are talking about a multi-fluid system, so we have electrons, we have molecules, we have different energy sources, so it is a complex system. And what we do is we try to answer this type of topics. So we help you achieve the highest profitability for your market. We help you understand the certification requirements depending on the project that you have. We help you also get public funding and be eligible, of course. And this is very important, the technical optimization part. Because at the end, considering all this information, we are able to optimize the system architecture with digital tools that we have developed in-house. It is also important for those of you that are participating maybe in a hydrogen hub to be aware that there is a huge issue, which is that you have to align more than 20 stakeholders per hub. So that's something very important, and of course has to do with the stakeholder alignment. Okay, let me explain now what's the systems engineering approach. What systems engineering is when you have a huge problem, when you have a complex problem, you try to break down the problem into subsystems, right? And you can have different subsystems and see how they interrelate and correlate to each other to be able to solve the problem as a whole in a holistic way. So what we see here is that we usually develop a methodology to solve the functional architecture, the logical architecture, and the physical architecture. And what I mean by this is that the functional architecture defines what you are going to produce. Are we talking about methanol? Are we talking about ammonia? Are we talking about e-kerosene? You can have one off-taker, you can have multiple off-takers. So so those type of things are what we solve here. Then we have the logical architecture. By logical architecture, what I mean is the process from which you go from one raw material and you produce something different, right? And then we have the Fischer-Tropsch reaction, we have the direct air capture, we have the methanol to kerosene, the Haber-Bosch process, and so on. And then we have the physical architecture, which is nothing else but where we are going to install the plant, right? You can produce hydrogen and have your facilities close to renewable energy. You can have it also close to the port. You can have a pipeline or transmission lines, right? That depending on what's more convenient to transport. So those are the type of things that we develop with the physical architecture. And then what you just have is you end up with a decision tree in which, let's say we have a project in a location. We don't know if we want to produce ammonia, methanol, or e-kerosene. and then we go, okay, if it's ammonia, I could do it for 2030 or 2035, and things are going to change, right? You have new technologies, you have cost reduction curves, and so on. And this is how we end up with an entire decision tree that ends up in many trade-off studies, okay? So you have to do many trade-off studies to know the best way to solve your project. So let's go now to the case study. The objective is always to start, let's consider that we need to produce a hydrogen and meet some local, national, and maybe a potential international demand, okay? And then what you want to end up with is a robust system that is able to comply with all your clients' requirements that come from the regulatory framework from which your client belongs to. Step one, there are many stakeholders here. What we can see clearly is that, for example, if your project is connected to the grid, you will have to talk to the TSO, right? And you will have to comply with all its requirements. Then we might have to talk also with an international off-taker because they need a certain attributes that maybe you are not complying with, so you need to know them better. The same could happen with the environmental authorities, which affects a lot for the permitting process. Then we have the step two. And what this means is that you can convert all these needs into design criteria, right? And these are many design criteria that can come from a stakeholder that I just presented. So here is the part in which you say, okay, I have this design criteria, these are my options, and then you go to step three, you formulate your scenarios, you define your cases, right? Am I going to produce 100% renewable, 70% renewable? Am I going to produce two different molecules? And you end up with step four, which we are absolutely sure that this is necessary to solve this type of complex projects, which is to digitalize all the modeling and the whole definition process. Because it's very difficult for systems like this to work in Excel sheet, right? And therefore, you need to use powerful tools that are able to optimize these systems. And for that, we have Andrea, we have Dieter, which is a data analysis cost, and land eligibility analysis, mobility optimization software. So depending on the application you need. If you want to know more about them, we can discuss them later. So now consider that you have a fixed size hydrogen production plant. So that means that this part is already fixed. And then you have upstream degrees of freedom and you have downstream degrees of freedom, okay? So the question here is, how can the architecture integrate a hybrid power system that has the grid, the PV power plant, the wind farm, how you can integrate it with a system that wants to produce hydrogen for a refinery and for a natural gas grid, okay? That's the main question here. And the answer is you have to look at a hourly stamp, okay? So you know that a refinery operates in a stationary process. So you need a minimum of hydrogen at any moment that has to be there. And then you can also, and then if you produce more, which is what we can see on the right side, you see that when you have PV and wind, what you do is you inject to the refinery, you can put everything else in the natural gas grid, and also you charge your hydrogen storage. So this is the type of analysis that you have to see. And you can make it more complex. What happens now if you also need to export ammonia and you want to provide ammonia locally, or you want to produce liquid hydrogen and you want to export it? Well, those are the type of questions that can be solved when you look not only at a yearly, in a yearly basis, not only in a monthly basis even, but at an hourly basis, because you have to know the dispatch of all your plants, okay? So that's very important. It behaves different in summer than in winter, and there are many decisions to take there. So this approach has been used in more than 100 projects already, and these 100 projects accounts for more than 5 billion. And we have about 50 experts between engineers and also economists that are doing this, developing projects in all these parts of the world. Thank you very much. If you want to further discuss, you can add me on LinkedIn with the QR below, and we will be happy also to attend any question at our booth. Thank you.